In the first tech challenge, students learn to think like engineers. Teams of up to 15 members from grades 7 to 12 design, build, code, and compete in an alliance format against other teams. These robots are built using a reusable platform powered by Android technology and can be coded using a variety of levels of Java-based programming. Guided by adult coaches and mentors, students develop STEM skills and practice engineering principles while realizing the value of hard work, innovation, and working as a team. But folks, it's more than just building robots. Teams design and build robots, raise funds, design and market their team brand, and do community outreach to earn specific awards. Participants are eligible to apply for over $80 million in scholarships. All right, let's see. On the left side, we got team 16417, Dr. X Academy. And on the right side, team 18844, the Pro Teams. All right, not wasting any time here, starting this match in 3, 2, 1, whack.
Hard to believe it's already our final match. We'll have to see how these teams come out here in this final match. Proteins and Dr. X Academy, both of them already have the ducks off of the carousels and have already dropped off that marked box onto the top of the team shipping hub. Dr. X Academy already makes another round into the warehouse to grab more freight. They're going to grab another box, and actually they're putting it on that middle level, whereas the Proteins are going for the top level of the shipping hub. Interesting to see strategy differences already playing out. Dr. X Academy back with a third piece of freight, and now they're already going back to the warehouse as
drivers, pick up your controllers. 3, 2, 1.
So you already saw some differences in strategies at the beginning of that autonomous period there. Dr. X Academy was placing boxes on that middle hub so they could get more boxes in, whereas the Proteins were going for that top hub, which meant more time to line up. But now look at how the speed of these two robots. My goodness, you can see just really the cycles going around. Neither robot going over that barrier, but it doesn't matter because you can see just the speed of these drivetrains and just how effective they are. Proteins are going to drop a box, but that's okay. Look at the speed of this robot. They'll be able to make it up in no time. Dr. X Academy, they're back and grabbing more. Proteins drop their second box. They're going to have to slow down maybe a little bit to figure out how to get those on in time as we were moving on. But their cycles to and from the warehouse are intensely quick. Dr. X Academy, you'll notice their robot is like doing that little bit of a turn. It's got just the right combination of wheels to move around so that robot doesn't really have to maneuver around too much. The Proteins doing kind of the same thing, but they do have to do a full turn, which means they're not quite as lined up. Whereas Dr. X Academy, they got that nice, controlled motion as they're moving around. That being said, the Proteins are definitely moving a lot faster from the warehouse to the top of the shipping hub. So it's very interesting to see these differences in strategies play out like we've been talking about all day. Proteins, they're doing 2 cycles at a time, and it's just insane to see as they're going back to grab more. You can see the warehouses are starting to look a little bit depleted, and they're all backed up against the wall for the Proteins while they're still stacking on top. Dr. X Academy is doing a really good job of keeping that shipping hub kind of level throughout this entire match. It looks like they're going to grab their team shipping element here, and so are the Proteins. We got double team shipping elements. They're going to the top of the shipping hubs. Yeah, it looks like both of them are stacked on top, and Dr. X Academy speeds over to the carousel, followed closely by the Proteins. These guys want ducks on the floor, and they want them now, so they're heading to those carousels to get it done. Just look at the speed at which the carousels are being turned. These teams got high energy gearboxes ready to go here. The Proteins are going to drop a duck on the floor, but that's okay. They still got plenty of them. The human player is going to pick that up and be able to put that back on the field. Oh no, they drop it again, but the Proteins are going to decide to go and aim for the warehouse. Both teams aiming for that warehouse. It looks like they just got in as time expired. Wow, Karthik, that was an insane final match to see. Those great teams on both sides, the differing strategies, everything, the culmination of what we've been talking about today. Karthik, can we see some scores?
Oh, we can, and you're right, Connor. We definitely finished with a bang or maybe a big giant quack, because those were some fantastic matches right there. All right, taking a look at these scores on the left side, highest submitted score from Dr. X Academy, team 16417 was 185. Our next award is the Control Award, sponsored by ARM Incorporated. Control Award celebrates the team that demonstrates innovative thinking in the control system to solve challenges such as autonomous operation, enhancing mechanical systems with intelligent control, or using sensors to better achieve results on the field. And here's what the judges have to say about the winner of this award. This team's unique and robust use of a variety of algorithms really caught the judges' attention. This team's academic implementation of everything from S-curves to S-curves to advanced position estimation gave them precise control of their robot. Their complex implementation of programming functions helped easily solve for X. The control award goes to team number 16417, Dr. X Academy from Toronto, Ontario. Now, it's time to announce the two teams who have qualified for the first championship in Houston in April. These teams were selected based on the official First Tech Challenge advancement criteria. Our first team advancing from Ontario is team number 16397, Relatively Quantum. And our next team is 16417, Dr. X Academy. Congratulations to these teams. More details will follow.
In order for our robot to move to positions precisely and effectively, we created a function that helps determine our global position relative to our starting point, and another function that uses this calculated position to control our robot. So to determine the global position relative to our starting point, we initialize a class called Position Estimation that publicly shares the coordinates of the robot at any point in the program. This runs on a separate thread and uses an algorithm called dead reckoning, which converts polar coordinates to xy values over each interval and returns the summation of x and y. After we find the global position, we put the coordinates and heading angle inside the position control class. This class basically encodes the mechanism control kinematics within a Jacobian matrix so that we can transform our desired heading vector into 4 different wheel speeds by simply multiplying our desired heading with the Jacobian matrix.
We have attached a color sensor to the bottom of the robot, detecting the white tape at the entrance of the warehouse. If the sensor detects the tape, it overrides and resets its estimated position.
The S-curve motion planner is a set of equations that allow control over the jerk of the robot. It is preferable over the regular trapezoidal motion planner, and it allows for very precise movements. Instead of using time as a variable and seen in the first graph, I found the inverse displacement and solved for time so that I could find my velocity at any distance. The process of constructing and implementing these set of equations can be found in a document on our engineering notebook.